Okay, so in this example we have a little simple mechanism comprised of two links which are lying in contact with some vertical and horizontal surfaces respectively. And we're given a little information about point A, namely its velocity, and we're asked to use this to determine the speed of end C of link BC. Okay, so the way I'm going to do this is I'm going to start by identifying what I know the most about. In this case I know the most about link AB. Namely, I know the velocity at one point, A identically, and I know the direction of velocity, at least in a plus or minus sense, for a second point, B. Namely, I know it has to move along this horizontal path. So if I know the velocity of one point identically and the direction of velocity of a second point, I can go ahead and sketch in construction lines, which are perpendicular to those, and try to locate the instantaneous center of that bar. And if I do so, I'll realize quite quickly that the instantaneous center of that bar will be somewhere like right here. In addition, I can use a little bit of math and say, well, given that this angle right here is phi, I know this interior angle here is phi, and this must be a triangle with given by L times the cosine of the angle phi on this side and L times the sine of the angle phi on this side. Now this is very useful because I can start to do some useful math on the system now. Namely, I could say, for example, that the angular speed of link AB has to equal the speed of point A divided by the distance between point A and the instantaneous center of the bar. If I go ahead and do some substitution here, this means that omega AB will equal VA, a known quantity, divided by L times the cosine of the angle phi. Once I have that in place, I can use that to find the speed of point B. Namely, I can say the speed of point B is equal to, in this case, omega AB, times the distance between point B and the instantaneous center at point AB. If I do some substitution here, this will give me VA divided by L times the cosine of phi times the distance, which is L times the sine of the angle phi. This, of course, says, noting that the L's cancel, that VB is going to equal VA times the tangent of the angle phi. Now I can also use this information to come up with some directions. Namely, we can note that if AB is rotating about the instant center as shown, that the omega of that bar has to be moving in a counterclockwise sense, and that if I extend this, then I know also the velocity of point B has to be towards the right. Now that I know the velocity of one point on point B identically, or bar BC identically, and I know the direction of velocity, at least in a plus or minus sense, of a second point, namely point C, I can sketch in a second set of construction lines. If I do so, I'll end up with the triangle shown and an instantaneous center for bar BC, which is directly above the previous instantaneous center. In addition, if I note here that this interior angle is theta, then I can say this interior angle here is theta, and I can say then that the total length right here will be L times the cosine of the angle theta, and the total length of this side right here will be L times the sine of the angle theta. I can then use this information to try to find something out about the speed of point C. To start, I'll note that the angular speed of BC will equal VB divided by the distance between point B and the instantaneous center of bar BC. If I work this out, this is going to give me VB, which is VA times the tangent of the angle phi, divided by L times the sine of the angle theta. I can then use that to find the velocity of point C, or more accurately its speed, which is all I'm asked for, by noting that the speed, VC, will equal omega BC times the distance between point C and the instantaneous center of bar BC. And if I do some substitution here, this is going to give me VA times the tangent of the angle phi divided by L times the sine of the angle theta times, in this case, L times the cosine of the angle theta. In this case, the L's are going to cancel out, and what I'll end up with is that the speed VC is equal to VA times the tangent of the angle phi divided by the tangent of the angle theta. From here you can just plug in numerical values for VA as well as phi and theta and get your final result. Best of luck.